I'm going to turn off my mic.
Oh, recording in progress. Okay. Shall I start?
I hear myself. I'm not sure if I'm hearing you on the speakers here, right?
Can you hear me?
I hear you
Can
on
you
the
hear me?
computer. Let's see, just a second. If I turn this off, so I hear myself. Can you speak?
Hello? Can you hear me?
Okay, we do hear you. Okay. So
Okay.
I'm gonna turn up the volume a bit and then you can get started.
Okay, great. So I made some rough slides just because I wanted to get everything in the right order. I think, have you already had a session where you talked about another family of examples of symplectic singularities?
We had, I'll tell you.
Yeah, there's some sort of echo.
We had some examples, but I'm not sure if it's the ones that you want.
Okay, so I'm going to just maybe talk about some history, but it's probably in the wrong order. But this is the way I remember things. So there's no classification in general of symplectic singularities. In dimension 2, there is. It's the ADE classification. So finding or duval. So the dimension 2 case is extremely well understood. Hold on, let me. Right, okay. And so the question is, what about dimension 4? Now, I actually need to realize that this is the wrong ratio. Are we going to see? Yeah, okay, that's fine. What about dimension greater to 4? Well, you have the minimal nilpotent orbit closures. So the first thing that you would do, any symplectic singularity has, a set of strata, and you can take slices between strata. So the first thing that you would do is think about, well, suppose you have a slice between adjacent strata. What singularity could that be? So that's going to be, if it's normal, it's going to be an isolated symplectic singularity, and in most conditions, it's going to be conical. So this is why you might first of all ask, well, do we have a classification or even a kind of conjectural classification of the isolated conical symplectic singularities of arbitrary dimension? So the families, the known families, and this is going back to kind of the prehistory of the subject. The known families are, we have the minimal nilpotent orbit closures. These are called minimal singularities in the Dr. Chazy sequence of papers. We can also take the quotient, so the orbit space of any one of these minimal singularities by an action of a finite group. But that will only be isolated if gamma acts freely away from the origin. So otherwise, whenever you have a non-trivial stabilizer, you'll get a singular point of the quotient. So whenever gamma acts freely on the minimal nilpotent orbit itself, then we get an isolated singularity. Okay, and the thing that you notice about these is if you have an isolated singularity and you remove the singular point, so you might want to ask, what is the fundamental group of that smooth part? So that's the local fundamental group. So for the minimal singularities, with the exception of type C, these are always locally simply connected, so there are no covers. Type C is different. It's as you can see there, it's got fundamental group S2. But any one of these quotients are going to have a non-trivial fundamental group, local fundamental group. And so you can think of that as saying, well, there's some cover. Well, obviously there's a cover. It's the minimal nilpotent orbit closure.
Oh, sorry.
So you're echoing. So is it best if I turn my own? I'll tell you what I'm going to do. I'm going to put some headphones on. 1 second.
Is that better? Let's see. Can you hear that? So Amihai had a question. It's just that it echoes.
Okay, sorry. On you go. Yeah. What was the question?
All right. Now Amihai had a question. Let's try it that way. So what's the question?
Does it have an example slice which is a form minimal a divided by z2?
So yeah, he wants an example of a slice minimal a divided by z2. Yes.
Well, so I guess first of all, the Z2 action is not, uniquely defined. So we will come later to an example of an A2 quotiented by a cyclic group of order 2. But if you just, I guess what you're
The one
asking
that
about
preserves the
is a larger
antisymmetric
singularity
form,
which
Amihai
has a
says.
slice inside it that looks like that. And so, yeah, I could cook up examples, but here I'm just saying, suppose you have an isolated singularity. Well, here are some examples of isolated singularities.
So I don't think we got the answer to that last question. I could you tell us once more about this? The question was the Z2 action preserving the antisymmetric form.
On preserving the symplectic form. So any Algebra automorphism will do that.
Makes a to SO.
Yeah, the one that breaks A to SO.
Yeah. So if you're so if you want a free action, like this second bullet point here, then it has to be the involution with fixed points SO. So then there's a unique involution in that case. But you could have a Z2 action which has some fixed points. But for an action which has an isolated singularity, it has to be the involution with fixed points. That's how.
Okay, thanks.
And that does appear. I can show you exactly where, but that does appear once in a nilpotent cone of type E7, and A2 over that Russian. So that will feature later on a couple of times. That's one of our friends. Okay. So some other examples of isolated symplectic singularities. So we can also just take a vector space quoted by a finite group, a finite subgroup of SP2M. And so for this to be isolated, it needs to act freely away from the origin, which is quite a restriction. And then going back to around 2007, I think it is, there's this paper of Ostrich, Malkin, and Vibornov, which looked at affine Grassmannians, and they found these singularities that they called quasi-minimal singularities. Right, it's a bit. I'm hearing my own voice, so that didn't happen when I had it through the speaker. So I'm going to switch back. But if you ask me a question, I'll put the headphones on again to avoid the echo.
All right. Do you hear us still?
Right. Okay. Can you hear me?
Yes. Do you still hear us as well?
Yeah. Let me turn it up a bit. Yeah.
Perfect.
Okay. So those are some examples. Now, around 2005, 2006, I was working with the FJLS team that I think some of you are familiar with, Fujita and Thomas, and we were classifying singularities in exceptional Lie algebras associated to adjacent pairs. So the famous sort of Krafft-Puchesi work, which looked at the classical Lie algebras, we were doing the exceptional types. You take a pair of nilpotent orbits. One is contained in the closure of the other, and there are no orbits in between in the partial order. And then you look at a Sloterdijk slice to an element of the lower orbit, and you intersect with the orbit above. Right. So this, as long as it's normal, this is a symplectic singularity, and the normalization is always a symplectic singularity, an isolated symplectic singularity, because that Sloterdijk slice. So the only point which belongs to the lower orbit is the element E itself, right? So if you just ignore issues around normalization, then it turns out that there aren't very many possibilities here. So in classical types, this is always either a minimal singularity or a Kleinian singularity. And so in exceptional types, that's almost true. Again, there's interesting stuff to do with branching and non-normal singularities arising, but if you ignore that, it's always Kleinian or minimal. In fact, there's one thing I should add: it can be smooth once you take the normalization, but otherwise, it's always a known thing, with three exceptions. Once in type E6, once in type E7, and once in type E8. So the thing in type E6, there's a slice which gives you quotient of four-dimensional vector space by free action of a cyclic group of order 3. And in type E7, I said we would say this is one of our friends. We have a quotient of the minimal nilpotent orbit closure in SL3 by an outer involution. And so this is an isolated singularity. And it occurs once, and when you kind of really dig into the nilpotent orbits in exceptional Lie algebras, you find that there are sort of coincidences between what Lustig called, did he call them the exceptional nilpotent orbits or something, which have, you know, when you look at the Springer correspondence, they come up with strange, you know, these kind of representations that satisfy unusual properties. Anyway, so that A2 over S2 occurs once in E7, and then there was a singularity that we found quite hard to identify that we denoted chi, and so this does not match. It's not. We knew that it isn't a minimal singularity and it isn't a Kleinian singularity, but we couldn't first work out what it was, and you can check by looking at transverse slices that it embeds into a sum of SL2 and the fifth symmetric power of the natural representation for SL2. Now, as we'll see in a moment, that is quite similar to the quotient of C4 by a dihedral group of order 10. But that quotient has three strata. It's not an isolated singularity because there are reflections that fix points in.
Why does that suggest C4 mod die 10?
1 second. Hit me again. Yeah, what's the question?
Why does it suggest C4 mod die 10?
Oh, just because, as we'll see, this embedding in SL2 plus S5V, we have a similar embedding for this quotient. But we'll also see that there's a degree issue that doesn't quite match. So, yeah, I'll explain this in a moment. In fact, on the next slide. Okay, right, so let Wn denote, this is consistent with the paper that I'm referring to that I haven't written down, but it's BBFJLS. This is the paper that we're referring to. So Bellamy, Cedric Bonafé, Foujuto, Levy Summers, that Travis sent the link to the archive version. So the notation there is WD. Let's use N. WN is a dihedral group of order 2N. And we're thinking of it as a reflection group. So this is another notation for the same thing, GNN2. Explicitly, it's the group generated by these matrices when acting on U. And it's really straightforward to work out what the invariants or a set of generators for the invariants for this group. You take the Slakely subgroup first of all, and then you look at the action of the S2 on top of that. And so we have a list of generators as follows. There are 3 of them of degree 2, and then there are n+1 of degree n. And so you could sort of do this by hand. It's certainly clear that these are all invariants, and then it's not too difficult to show that they generate the full invariant ring. Now, let me see, is it the next slide? So yeah, so the E, Q, and Q are of degree 2, and then the other ones are of degree n. So I'll come back to that in a moment. But I'll point out that the E, Q, and Q kind of they span a copy of SL2, and these AI span a copy of the n+1 dimensional irreducible for that SL2. Okay, and we have a list of relations. Now the relations are not necessarily that illuminating, but they give you an idea for. I mean, you could use the relations to come up with a Hilbert series, for example, of this coordinate ring. So first of all, we have a kind of a relation which is in degree 1 for the generators of degree 2 and 1 for the generators of degree n. So they're kind of separate creatures, really. And then we have another one which is, or a set of relations which is quadratic in the A, J, A, K. Okay, then you notice that the z squared minus 4q cubed pops up. Okay, and I'll come back to that. Now, so if you write the E, Q, and Q, these letters were chosen by Cedric Bonafé, but maybe not. Yeah, okay, you might want to choose different letters if you're a bit confused by them. If we put E, Q, and Q into an SL2, then that E squared minus 4QQ is just the determinant. And that's kind of the right way to think about these. And if you go back to the generators of the original coordinate ring on C4, then another way to think about this determinant is the square of this semi-invariant. I'll come back to that a bit later as well. Okay, so we've got an SL2 given by the generators of degree 2, and then it's not too hard to see that the elements of degree n span a copy of this SNV. So this goes back to what I was saying. If you have n equal to 5, this says that there's an inclusion of the quotient into SL2 plus S5V. Okay, which here I said this chi embeds into SL2 plus S5V. So it's almost consistent with that, but there's an issue, because in addition to this SL2 orbit structure, there's a scaling action coming from the degrees of these generators, and so the weight is just given by the degree. So the weight for this GM action is 2 on the elements of SL2 and n on the elements of SNV. So if you're, so Amy probably thinks about the Hilbert series. So the Hilbert series is just going to be, well, I'm going to have 1 over 1 minus t squared cubed coming from the SL2, the 3 free generators of SL2. And then I'm going to have n plus 1 t to the n. They're coming from these generators of degree n, right? So that the Hilbert series is giving you the GM action. It's just the degree of the for the power of t. Okay, and the thing about the singularity chi is that instead of having an S5V in degree 5s, they turned out to be degree 3, which took a little while to understand. Okay, but let's just point out something, which is that if you just look at the relations and consider the SL2 action, in fact, there are finite
Sorry, we have a
orbits.
question.
Okay, go on. Yes.
What is it?
There is a mismatch by 2 for any n.
There's a mismatch by 2 for any Ami-Heisen's?
Yeah, I'll talk about these new singularities y of n in a moment. So at the moment, we're just looking at the quotient, and yeah, you have it's a 1 plus 3t squared plus 6t to the fourth, etc., coming from the generator's degree 2 plus n plus 1 t to the n and some other terms, right? So that's the Hilbert series for the quotient, and the quotient is I can't quite do this curly qn, but that's and the point is that for the y of n, this t of n is going to be t to the n minus 2. So for chi, we have 1 plus 3t squared plus 6t cubed instead of t to the 5. So it gets shifted.
Yes. Okay. Yes. Thank you.
Okay.
Okay. So in fact, there's an open orbit. So this turns out to be quite a useful way sometimes to think about these singularities where you have a large symmetry group. So the SL2 doesn't act on the singularity with finitely many orbits, but once you factor in the scaling action, it does, because any semi-simple element, then any non-zero semi-simple element is going to be conjugate to this this diagonal thing. So in fact, there turns out to be an open orbit, an orbit of dimension 4. So you can use this to show an isomorphism of something with this quotient, for example. Okay, so there's an open orbit there. And now you can write down the singular locus, and it's already almost half past, so I'm not sure how much detail I should give of this singular locus. But you know, the singular locus is given by the image in the quotient of any v which has a non-trivial stabilizer. But here we've got a reflection group acting on u plus u star. So the only non-trivial stabilizers are when points are fixed by a reflection in the dihedral group. And we know what the reflections are. Those are the off-diagonal elements of the dihedral group. So you can use that to write down some polynomials that vanish on the singular locus. So it's so any semi-invariant will vanish on the singular locus. And here's a really kind of obvious semi-invariant, xx minus yy. This is fixed by the cyclic subgroup of the dihedral group, and it's a -1 eigenvector for any one of the reflections. And so in fact, the following polynomials vanish on the singular locus. I take the square of this this thing. This is a kind of discriminant. And then I take this xx minus yy times any one of these these look like a I, but I've got a minus sign instead of plus, right? So each one of these is 0 on the singular locus. And we've also got d, bg, bj, bk, but now this won't have this xx minus yy term. So d, I didn't have space for it. This is x to the n minus j, y to the j minus y to the n minus j, x to the j, times the same thing for k. Okay. Okay, so this is maybe sort of more detail than you need, but the point is that this gives you the ideal which vanishes on the singular lockers. It's given by all of these terms here, and it's written in a convenient form because the d, you know, is kind of always featuring. And so if you blow up this ideal, that's the same thing as blowing up this slightly smaller ideal. And so in a moment, I'm going to talk about that blow up. So one thing to point out is that there's a dichotomy between the case of n even and n odd. So when n is odd, all of the reflections are conjugate. And so the singular locus is irreducible. But when n is even, there are two conjugacy classes of reflections. So there are two irreducible components. And you can see that because these terms factorize. So, and this will be important later on. Okay, so then what you do is you want to resolve this singularity, and so an obvious choice is to just take the singular locus and blow it up. That doesn't always work. That's not always crappant, but in this case it does. It does give you a partial resolution of the singularity. It's crappant, so you have a symplectic form on the blow up, on the smooth part of the blow up. So sorry, repeat the question, please.
How can you ensure this not?
Sorry, I didn't quite hear that. How can you?
How do you ensure the blow up is symplectic?
I mean, that's a good question in general, and I don't know the answer. You have this machinery that says there exists a Q factorial terminalization, and each of the steps to obtain that is a blow up, but it's not clear to me what you would choose to blow up. In this case, I mean, I didn't know about that machinery at the time. I just said, well, let's blow up the singular locus and see what you get. And it turns out that it's symplectic. It's a symplectic singularity. So the symplectic form lifts, well, extends to the smooth part of the blow up. Does that answer the question?
I mean, I guess that you know that if the Poisson structure extends, it's still going to be a symplectic singularity, right?
Yeah, that's exactly. Well, you need the extension to be symplectic, so it needs to. Yeah, I think that's right. The Poisson, if the Poisson bracket extends to the coordinate ring of one of the affine neighborhoods in the blow-up, then yeah, that I think that's what you need. But a priori, I don't know a way to see, given an ideal, whether that will, you know, there's whether it will be crappant, which is the same thing as saying that the symplectic form extends to a symplectic form on the smooth part.
Okay.
Okay. Right. So the blow-up embeds as a closed subset of the original singularity crossed with this projective space coming from the these projective coordinates over here. And so the first affine open in particular is given by, you basically set this coordinate equal to 1, so you're dividing everything by d, right? And so we can see the first affine open is going to be an affine variety with generators E, Q, or the coordinate ring has generators the E, Q, and Q. I'm being slightly sloppy about generators of the coordinate ring versus values, but it's okay, I think. So and we're going to have these BI in this coordinate ring here. And in fact, once you have the BI, you already get the AI. There's a sort of straightforward relation that describes these AI in terms of the BI. Right, so let's move on. So that you notice that we've still got the SL2 here, and then we've got these BI, which also generate a copy of SNV, but the degree now is, so if you look at DBI, that's, where's it gone? Here, that's of degree n+2, right? And D has degree 4. So BI itself has degree n-2, okay? So you notice you've got an SL2 and an SNV, but now the scaling action on this SNV has degree n-2 rather than n. And that exactly matches the chi in the case n equal to 5. We've got this degree 3 thing here, right, rather than degree 5. So it's certainly, I think this is the thing that I spotted that made me think, we might be able to get this chi singularity in terms of some sort of blow up of the quotient singularity. Otherwise, it's quite similar. We also have an open orbit. The open orbit looks quite similar. We have relations which also look quite similar to the relations that we had for the quotient singularity, except this factor of e squared minus 4qq no longer appears the way it did there. And the fact that this is not there means that it increases the number of smooth points. So you end up with a singularity at 0, but all of the points are smooth. So if you think you had, for the quotient singularity, you had 3 strata. You had 0, and then you had the other singular points, where you had either 1 or 2 irreducible components, and then the smooth points. Now the non-zero singular points, if you take a transverse slice through one of those, then it's just an A1 singularity, right? A C2 over plus or minus 1. So you would expect, or you would certainly hope, that a single blow-up will resolve those singular points. And what's not clear is what happens to the preimage of 0 in that blow-up. But the point is that here, the preimage of 0, with the exception of that one point, this is also smooth. Okay, so this we've got from something with a 2-dimensional singular locus to a singularity which is isolated. And in fact, all of the other affine opens are smooth. So there's some nice special cases that help to understand what's going on. So for n equal to 3, in fact, this doesn't have a singular point, it's smooth. So the y of 3 is just a vector space. And so blowing up C4 over this dihedral group of order 6. Now, a dihedral group of order 6 is the same thing as S3, right? So we've blown up 4-dimensional vector space over S3. This is H plus H star over S3. And blowing up once at the singular locus resolves singularities, and it's well known that if I take the analogous thing for any symmetric group, I have a resolution. And so we've just rediscovered the Hilbert-Chow resolution. Now, what about n equal to 4? Well, in this case, your generators BI have degree 2 rather than 1. So that means both the SL2 and the S4V, these are all of degree 2. So this is a homogeneous thing, and all generators of degree 2. So what you would imagine is this is probably a minimal nilpotent orbit closure. And in fact, that's right. This is an SL3. This is a minimal in SL3, so an A2 singularity. And so this can be, so the minimal nilpotent orbit closure in in A2, there are two ways of resolving singularities given by the two conjugacy classes of maximal parabolic. And so we have some further blow-ups, in fact, two possible further blow-ups that will resolve singularities here. But that shows that we haven't necessarily finished. And in fact, when n is even, this y of n, when I say we haven't necessarily finished, the right way to think about this is to look for a q factorial terminalization. So this singularity is not q factorial. And when n is even, that's true of y of n. Okay. And so for n equal to 5, we get the singularity time, which appears in the nilpotent cone of E8. So, okay, so the first two special cases are kind of interesting. Right, so we've been thinking about this in terms of this nilpotent cone of E8. But Cedric Bonafé and Gwyn Bellamy sort of separately had kind of been looking at deformations, so via symplectic reflection algebras, deformations of dihedral group quotient singularities. So you get these from symplectic reflection algebras. Colodro-Moses space gives you these parameters, and you look at the deformation coming from, you know, generic parameters in the parameter space. So specifically, they looked at the case of equal parameters, which is only really an issue when n is even. So I'll come back to that. But then if you look at a sort of generic value of the deformation parameter, you get a singularity which looks quite similar to the original quotient singularity, but we've got this factor here. And then it turns out that in fact this has an isolated singularity which is you know, smoothly equivalent to y of n. So it's not isomorphic as an algebraic variety, but it is when you take completions. So in the world of classification of singularities, it's the same. Yeah, so that shows that y of n has symplectic singularities. So that if you look at the paper, that's the key step is to show that this is normal. Okay, and then there's another construction which is interesting if you're interested in nilpotent cones, which is where you take, for n greater or equal to 4, you take the 3 orbits at the very top of the partial order on nilpotent orbits in SLN. So we have the regular, the subregular, and then an orbit I'll call the sub-subregular. The subregular slice is an an-1 singularity, right? So this is C2 over a cyclic group of order n. And that cyclic group of order n is the same as the fundamental group of the regular orbit. So when you take the universal cover of the regular orbit, and then there's a standard construction which allows you to take a kind of closure of that universal cover in the same way that the closure of the orbit is the nilpotent cone. It turns out that this n-to-1 map kind of becomes the canonical n-to-1 cover from C2 to C2 over mu n. So that means that you take the universal cover of the regular orbit and then affinize it. So the pre-image of the subregular orbit becomes smooth. And so the singularities goes down to codimension 4. This that singularity is y of n. But this is quite a different kind of construction to the thing involving the dihedral group. But they turn out to be isomorphic. And so another way of saying it is if you just take the slice down to the subregular orbit, this is the quotient of y of n by a mu n. That's a cyclic group of order n, mu n. Okay, so there's two different constructions of the singularity. Now it's 11:45. Where am I? I think I'm okay. I'm sort of more or less on track. So I want to think about
what's the diagram of the last singularity?
sorry, I have to put my headphones on. Can you repeat the question, please?
The question is, what's the Hasse diagram for the last singularity?
For this yn over mu n. Is that the question?
Yes, yes.
Yeah, it's just the Hasse diagram of nilpotent orbits at the very top of the nilpotent cone of SLN. So this is C2 over mu n, and this is what I need to remove one column. C2 over mu n minus 2.
An minus 1 and an minus 2. Yeah.
Sorry,
Minus 2.
so you have a
Is this what's written?
We have a hard time reading your
sorry.
paper. It's
Okay.
just so small on our screen. Just
Yeah,
if you could tell us what's written
pin
there.
it and unpin it. So this is a C2 over mu n,
Yeah.
and this is C2 over mu n minus 2.
Right.
Okay.
So it goes by 2.
Yeah.
And I think the sort of interesting thing is you can actually write down what this action is here. So the mu n is the diagonal subgroup of SL2. So you would never look at this slice and be able to say, oh, it's a quotient or something. It doesn't. It's not at all clear, but it's a consequence of this description as the cover. I can't remember how we thought of that, but yeah. Anyway. Okay, so Nomikawa's Veil group. So if you're interested in, so any symplectic singularity has a nice space parameterizing the deformations, and a very similar nice space parameterizing the resolutions. So it's the second cohomology, but when you're dealing with a quotient singularity by a finite group, this is also the sort of C in the construction of the symplectic reflection algebra. So I'm going to come back to the possible deformations / resolutions in a moment. But the Veil group, Nomikawa's Veil group, essentially it's describing the irreducible components of the singular locus of codimension 2. So in this case, it's corresponding to the conjugacy classes of reflections. And so for n odd, as I said earlier, there's a unique conjugacy class of reflections. And that means that the Nomikawa's Veil group is S2 and it acts on a vector space of dimension 1. Right? There's a one-dimensional space, whether you're over C or over Q or R. And so in the space H2YC, in general, you have these hyperplanes, and the deformations, if you've got a parameter landing on a hyperplane, those deformations are not going to be Q factorial terminal. But when you have a one-dimensional space, there are no hyperplanes except for 0, right? So that means that any non-zero parameter will give you a Q factorial terminal deformation of the singularity, right? So in the case of n odd, because there's this local analytic isomorphism between y of n and a deformation, that means that y of n is Q factorial terminal. So in particular, y of 5, so this chi is Q factorial terminal. And so that's as good as you can get. Okay, there are no further resolutions, for example.
Back to the previous point.
Sorry, what was the question?
The CN cover of regular orbit is symplectic singularity.
Travis, can you repeat the question? I can't quite hear in there.
Sorry, can you say it again?
So going to the previous the description that we have.
Yeah.
Is the CN cover the regular orbit of SLN. Another symplectic singularity.
Yeah, he said that it was smooth, right? The cover of the slice to the regular orbit, to the subregular orbit. So you mean that the slice to the subregular orbit?
No, not the slice,
Ah.
the cover of the regular orbit.
The cover of the regular orbit itself. Oh,
Of the closure.
the cover of the nilpotent cone itself. I see. Yeah, that
Yeah.
you didn't say. You didn't say that was smooth. No,
No, it's smooth down to codimension 4.
smooth down to codimension 4 only.
Right. So singular locus is the pre-image of the closure of this subregular orbit. So if you look at the nilpotent cone as a whole, not cover, just the nilpotent cone, then the singular locus is the closure of the subregular orbit. But
Right.
in this cover,
Yeah, but by itself, it is a symplectic singularity, right?
Yes, yes, it's a symplectic singularity. This closure. Yes.
these covers are, symplectic singularities. That's a result of Pandishev, I think.
Yes, that was my question.
I just wanted to know if it was a symplectic singularity. Yes.
Yeah, it is, yeah.
Yeah.
Okay, so for n odd, this y of n is q factorial terminal, but for n even, the dimension of this space is 2. So when Cédric Bonafé and Wynne Bellamy were looking independently at these deformations, they considered the equal parameters case, which is not the generic deformation parameter. So there's a line given by x equal to y in C2, and we're only considering deformations on that line. Because there are 2 conjugacy classes of reflections, then the Namikawa vowel group is S2, S2. I'll come back to that. So the singular locus here has 2 irreducible components. And then there's a comment there about one of them coming from the quotient. This should be a curly Q of n. So instead of blowing up the whole singular locus, we could just pick one irreducible component and blow that up, and leave the other one alone. And that's allowed. And it turns out that this also gives you symplectic singularity. And the singular locus is, well, I have the strict transform of the second irreducible component, right? You have a free image of the second irreducible component. It's going to contain exceptional fibers to blow up, and then this strict transform. And I also get one other singular clump. And in fact, if you do the calculation, it turns out this strict transform of the second component, if you think about it, you've got, let me draw a picture. I'll try and draw it sort of quite large. So you've got your singularity, and inside you've got singular locus 1. Now I can't draw complex dimension 4, so I'm just going to. This is really intuitive and not at all correct geometrically. So, but it's indicating the idea. So we've got 2 irreducible components of the singular locus, sing1, sing2, and all along here we've got A1 singularities, and the same thing here. And then I've got this 0. And so what happens if you blow up one of the irreducible components? Well, if you ignore this 0, then it means that you've left the rest of this second irreducible component of the singular locus unchanged, right? This is not affected. And indeed, once you do that, the strict transform of this thing is just going to be basically a load of A1 singularities. So this 0 gets taken elsewhere, rather this singular point, the intersection gets taken elsewhere. The strict transform won't contain anything singular coming from that zero. So we get a bunch of A1 singularities, which are very easy to resolve. Just a single blow-up resolves a C2 over plus minus 1. So, so this process where you blow up one irreducible component and then you resolve the other one leaves you with an isolated singularity. And what is that isolated singularity? Well, it turns out that it's just y of m over S2. So n is equal to 2n. And so this thing here is, we've got a singular point which is not y of n anymore. It's y of m over S2. And we can specify the action unit. So that's still an isolated singularity. And we've got a unique singular point that looks like this, right? So I guess the question is, what is happening?
So is it obvious this is Q factorial, this singularity?
No. Why? How do I know it's Q factorial? Yeah, this may be a bit hand-wavy at this stage. So this is unpublished.
And this is independent of whether m is even or odd. This turns out to be Q factorial.
Yeah, it's strange. And in fact, I've got a comment about that. So if m is even, then y of m is not Q factorial, but the quotient is. The quotient by S2 is. And so I know one special case where I can show whether that is true. Okay, so I'll draw some graphs in a minute that explain maybe a little bit about what's going on there. But one thing to point out is that in Beauville's paper, he looks at local fundamental group. So he proves that if the projective tangent cone is smooth, then it has to be a minimal singularity. And then he says, well, let's look at the singularities with trivial local fundamental group and try and classify those. And in the paper BBF JLS, we spent some time showing that these y of n have trivial local fundamental group. But in this case, the Q factorial terminalization when n is even has local fundamental group S2. And so I think it suggests that the local fundamental group and the Q factorial terminalization are two very different things. You're not really, the classification by the minimal model program and this Q factorial terminalizations doesn't necessarily have much to do with fundamental group. So, okay. So if m is even, then y of m is not Q factorial, but the quotient is. And there's a partial resolution which has trivial local fundamental group, but the Q factorial terminalization doesn't. So just have I got 5 minutes to switch to, maybe I'll stop sharing or pause share. No, that didn't work. I'm going to stop sharing and maybe move to drawing a picture. So can you see my document camera here? This looks a bit bigger now. I don't know if you can pin it on your screen, Travis.
We can see that. Yeah.
Yeah, we see it.
Okay. So for the even case, I'm going to draw a picture which is the H2 space, right? It's two-dimensional, and
Travis, need to remove the screen.
Ah, all right.
it is a bit small, is it?
Just change the view. Yeah.
All right.
Is that better?
Now we can see better.
Right, okay. So the point is in this space, it's so if you take coefficients in R or Q, it's giving you deformations. And so the right way to think about that is you take a Q factorial terminalization, and then you have the Murray cone inside your Q factorial terminalization, which has a sort of chamber structure, and you're looking for, anyway. So the point is that I'm drawing things over R, but I think if the deformations is involving everything over C, and then the kind of a subset of this is going to give you the resolutions, right? So over C, I have 4 lines, and if the deformation parameter lands on one of those 4 lines, then the corresponding deformation is not Q factorial terminal. So the 4 lines are the x and y axes, and the line y equal to x and y equal to minus x. So the equal parameters case is exactly landing on this line y equal to x. Okay. Now, in the resolution setup, I need to take something like so the Murray cone is like the dominant. It's a fundamental Weyl chamber for the action of the Weyl group, right? So the Weyl group is S2, S2, but it's acting on 2 lines independently. So the region I'm interested in for the resolutions is the first quadrant, right? So this first quadrant going back to so there was a talk a couple of months ago by a student of David Ben's-V called Alberto San Miguel Maraney, and he has some work which classifies all of the partial credit resolutions of symplectic singularities. And so in previous work, Gwyn Bellamy, and then he had some joint work with you, Travis, and Ulrich Thiel had looked at the Q factorial terminalizations, and these come from you take the complement of the hyperplanes in the fundamental Weyl chamber, right? So there are 2 regions here that give you 2 Q factorial terminalizations of the of your quotient singularity, right? And what about the partial resolutions which are not Q factorial terminal? So you have 3 walls. So the partial resolutions. And so we've got 2 open chambers, which gives you 2 Q factorial terminalizations. Okay, and then we have 3 walls, and that's going to give you 3 partial resolutions which are not Q factorial terminal. And in this case, there's only one other face, which is 0, right? So 0 gives you Q of A, right? But what about these 3 walls? Well, The external walls give you partial resolutions which are not terminal, and otherwise, so internal walls give you partial resolutions which are not Q-factorial. So going back to this picture above, we can say exactly what the three walls correspond to. So if you're on the line y of x, y equal x, this is the partial resolution which comes from blowing up the whole singular locus, right? And if you're on one of these external walls, this is what you get from blowing up one of the components. Right? Sorry, that's a bit small, but that's Sing 1 and Sing 2. So, as I said, when you do that, you have a two-dimensional singular locus. So this is not terminal. Terminal means the singular locus is co-dimension at least 4. And so, if you do that, blow up one of the components, you get a thing which is not terminal, so it lies on the external wall. If you blow up the whole singular locus, the thing you get has an isolated singularity, so it is terminal. And from the outer walls, one further blow up gives you a Q factorial terminalization. So that's kind of my argument for why this y of m over S2 is Q factorial. But there's also a further route, which is once you've blown up the singular locus and you have your y of n, there are two options for further blowups you can take to give you a Q factorial terminalization. So there are two different sequences that land you in each of those two Q factorial terminalizations. So that took 8 minutes rather than 5, but I thought that was a nice demonstration of the combinatorics of the Morricone and how this gives you a complete sort of classification of these resolutions. Okay, thank you.
Okay, so was that the end of your talk then?
Yeah, I had a couple more slides that basically said that.
Okay.
Let's see. What? Yeah, that's basically what I was saying. So in the sort of, this Nabikawa Morricone setup, you start with the Q factorial terminalization, then you contract to move on to one of the walls. So there are these divisorial contractions and small contractions. So divisorial contractions where you take a divisor and contract it to a point. And so that's obviously going to give you something which has a well, that is going to give you something that has a large singular locus. And the small contractions are going to give you something which is not Q factorial. But yeah, so divisorial contractions move on to an external wall. Small contractions move on to one of these internal walls.
Mm-hmm.
Yeah.
Right. Okay. Yeah, I mean, I think that, isn't it true that if you look at if you look at a Q factorial terminalization and you look at the movable cone there, you're going to see all of the different modifications. So this doesn't require Alberto's work, but he was talking about, for example, computing the Namikawa-Val group of these partial resolutions and things like that, right? So what are we using of Alberto's work here?
So I think the first thing, which is there's a bijection between the faces and the partial resolutions.
Hmm.
So that is certainly written down in his paper.
Okay.
How much of that he proved or whether it was due to somebody else. But yeah, so given a partial resolution, I guess you're going to have a relative file group or something, which would probably an S2 on one of the walls.
Right. That's right. Yeah. Okay.
You can play this game for any one of these.
I guess whether you're
yeah.
I guess whether you're a symplectic quotient singularity or not, just in general, if you want to look at all of the birational modifications, so all of these internal walls where we're changing things outside of codimension 2 will be like that. I guess it's clear that those are just given by different cones of the movable cone, different Mori cones in there. But then if you want to take divisorial contractions, then you get to the boundary of the movable cone, then maybe it's not always immediate, that's not a priori immediate, you get all of them that way, but in the symplectic singularity case, I guess it follows from BCHM, right, that you're always dominated by a Q factorial terminalization.
BCHM.
So anyway, I guess I just think, I think that the fact that you can get all of the partial resolutions from Mori cones, I don't think you need Alberto's work for that.
No.
But I think anyway, the vowel groups of these things was one of the among other things that he computed.
Okay.
Okay, there are questions? Did you want to show this example? Or?
I think Chimhao has a proposal.
So is this okay? So I think Chun Hao has a question for you. I'm not sure how close related it is to your talk.
One thing to add, I just seen the final slide. So some special cases. For n equal to 4, we got an A2 singularity. That's y of 4 is a minimal A2, and you can resolve it in one of two ways. Well, that's yeah, I already talked about that earlier. But for n equal to 6, excuse me, then y then over S2 is a B2 singularity. So this is we're starting off with C4 over a dihedral group order 12, and Q factorial terminalization has an isolated, well, a unique point, which is a B2 singularity. So it doesn't have a symplectic resolution, but this is about as close as you can get to having a symplectic resolution. And then for n equal to 8, we get our old friend A2 over S2. This in fact arises as a Q factorial terminalization of this dihedral group of order 16 quotient. So yeah, I just thought it was interesting that both the E7 and E8 cases that come back to dihedral groups. For E8 it's a dihedral group of order 10, and for E7 it's dihedral group of order 16. So anyway, yeah, so sorry.
Sorry, so what you're telling us here is that you're getting back to this slice singularity you found in E7.
Yeah, so there is a slice singularity which is 8 over S2, and Ami asked about that. Can you have an AN quotiented by Z2? So this is that example for A2. Yeah.
But so in general, we're getting Q factorial terminal singularities of the form y of m for n odd and y of m mod S2 for every m. And I guess that
Yeah.
I guess that it's possible that other quotients also give you q factorial terminal singularities. I don't know, but those ones.
Yeah, I think you have to quotient by a group that contains this S2.
Any group that contains the S2.
Yeah.
But if you want it to still be q factorial terminal, then obviously you can't have any symplectic reflections.
Yes, you.
So you're looking at, or you're thinking of maybe this this S2, something containing S2 and contained in this group, cyclic group that you were looking at before or something. Or I guess you know what all of the symplectic automorphisms of this Y of M are.
Yeah, I mean, they have to be contained in SL2, right? So we've. I think it is something like the ADE classification. So.
But you don't have a whole automorphism action of SL2 on Y of M, right?
You do, yeah.
Oh, you do?
Yeah, that's. So for the finite quotients, you want finite subgroups of SL2, but they have to contain. This S2 is generated by minus the identity. So,
I see.
no, that's not true. That's true if M is odd.
But we have symplectic reflections in this SL2. Or things that fix something up.
Yeah, I'll have to think about that. I think that there's something interesting going on, but maybe it's not just from SL2, right?
But anyway, I guess like for example, when you go to the cyclic quotient that gave us the nilpotent cone before, that's not obviously q factorial terminal because we can resolve that.
No, yeah, that's right. Yeah. Yeah. So I don't know how many, I don't know what other options there are.
Okay. But anyway, the only ones that are simply connected locally, whatever the local fundamental group is trivial, whatever you want to call that, that's only the Y of M for M odd.
Yeah, there may not be very many more. Yeah.
Okay.
So this A2 mod S2 has SO3 symmetry.
I didn't quite hear the last. Does it have?
Does it have an SO3 symmetry? This A2 mod S2?
Yeah.
Yeah.
And where does it show for E7?
Does it appear on the E7, this SO2 symmetry, SO3 symmetry?
Yeah. Yes. Yeah. Yeah.
So there is a suspicion that this would be the slice for the hydrophilic quotient of three copies of the fundamental of E7 by E7.
I didn't quite hear the end of that. Could be the hyperplane.
So it's a slice for the hyperkähler quotient of the slice for
Three copies of fundamental
three copies of fundamental for E7 divided by E7, yeah.
So the 56 dimensional. Sorry.
It's three halves times 56.
3/2 times 56, you see.
Yeah, because the 56 is a symplectic representation. So I
Right.
can take half. So I need to count units of half. I can take 1/2 or 2/2.
So you take 3 56-dimensional symplectic, complex symplectic representations. So that's 3 times 56 in complex dimensions. And then you take quotient by E7, you say. So this hypercalar quotient, you're saying that you think that should be isomorphic to.
Yeah, I suspect that the lowest slice
Mhm.
from the origin
Mhm.
is this
The lowest slice of so the minimal leaf closure in this hypercalar quotient you think is this E7 singularity.
that. Can you say anything about it? Can Paul?
Do you know anything about that, Paul?
No. Why? Yeah, I mean, I'll ask Abby maybe why that representation is of interest.
Why is it of interest?
Yeah, for
It's
example.
Why-
it shows up in
yeah.
6 dimensions as a physics problem.
So in a 6-dimensional field theory, you say this shows up?
Uh,
Okay, I guess so. Do you have the Hasse diagram for that hypercalar quotient?
Um, we have a guess.
Mhm.
I don't know. I want to test it.
Okay. Just to make sure I understood, Paul, so this SL2 action, the group SL2 is acting on Y of M via this embedding into SL2 cross symmetric power of V. So it's acting on the V and by the adjoint action, you're saying, and then this is actually commuting with the embedding is stable under this action. Is what you're saying? Is that what you're saying?
yeah, this is. So the action of this S2, as I wrote down, is where is it? It acts trivial on SL2 and then is -1 on the BI. So that you can just look at it. That's clearly an automorphism. Certainly, of the abstract coordinate ring.
Okay, so that's the action of S2, but the action of the SL2, I was saying, is that's via this the adjoint action on SL2 and
Yeah,
just the vector representation on the
but
symmetric.
you're right that any cyclic group of order greater than 2 has they're certainly likely to have fixed points. So
I have to think about I guess we have to think about whether there's a codimension 2 fixed locus in this subspace, right? In the subset, but
yeah, I mean fixed points. Yeah.
but yeah, I guess maybe it does, and then in which case we wouldn't get an isolated singularity anymore, and it wouldn't be therefore terminal.
I think cyclic groups of order co-prime to M should be okay.
Cyclic groups of order co-prime to N, you're saying?
Yeah, or N, yeah.
Ah,
Anyway, I think there's some, yeah,
okay. So maybe there's some that will give you still an isolated singularity and others,
yeah.
most of them might not. But if it gives you an isolated singularity, then I guess you're saying that it might even be Q factorial as well, I guess.
Yeah, quotient singular. If you have a Q factorial thing, and you take a quotient by a finite group action, that's Q factorial.
Right. Yeah.
So
Yeah.
determine whether it's minimal.
Okay. This is not obvious to me. Is this obvious? Obviously, you can't have any codimension 2 fixed locus, but you're saying if you have a Q factorial thing and take a quotient by something with fixed locus and codimension at least 4, it's obvious that it's still Q factorial. Is that true?
Yeah, because if you have a divisor in the quotient, it's the image of a divisor in the unquotiented thing, and then you can just take the average by the group elements, or take the product. You know, if you have it's yeah, it's not necessarily Cartier, but some power of it is, and you then take the product. So it's
I see.
principal, and you take the product of the images by the group action. That gives you a principal divisor.
I see. Okay. All right. Should we have Chunhao? Should we have your? Should we try to put your question on? What is it?
He has a proposal for the figure.
Ah, okay. Well, should I show that? Let's try. Let's see.
You have the what you expecting.
Let's see here. View. Okay. So here we go. Do you see it? For us, it's mirror, of course, but we have the actual board here. So this is Chunhao's proposal for the quiver.
Just change the framing into the short mode.
That looks. I mean, I wouldn't be the person to ask, but it seems plausible.
This is supposed to be, if you take, so this is a quiver with a non-simply laced quiver there. And so we have this n multiplicity here, and we're taking the Coulomb branch for this non-simply laced quiver, and that's supposed to be the Zn cover of the regular. So this is not just the yn. So yn will appear as a slice in this Zn cover.
Y will be the first slice.
Yeah, the first slice, yeah. So
That's what you will get from
the top slice, yeah.
The right two nodes.
Okay, so one thing to point out is if you take n equal to 3,
Animal G2.
right, and I guess some of you already know this. If you take the nilpotent cone of S equal 3 and look at the mu3 cover of the regular orbit and take the affinization of that, that is the minimal singularity of type G2. So yeah, so this certainly
It passes the test.
Ah, I see. Because that's the correct one for G2. You're saying if we have just for n equal to 3, you say, so you have 1, 2, 1 with a 3.
The thing I've written here, that's what about n equal to 4?
So So the nilpotent cone has a quiver which is taking the last node and making it not simplest. The last edge is not simple.
I didn't quite hear that question.
So
Um.
the difference between the two quivers
Yeah, the difference between the two quivers.
is the simplest.
I need to
So
unmirror this
yeah,
perhaps.
if we have a quiver like this, so here is just a n multiplicity of simple list, and this will gives you the regular of SL, and then we change this into the non-simply list edge, and this will give you a ZN cover.
Okay.
Oh, I see. Right, because you use this Crowley-Bowlby trick or whatever. You turned the usual thing with the n framing into one with its n's, and now you're saying that changing these n arrows into a single non-simply laced one is supposed to give you the cover. Why is that?
I think this is based on Hilbert series calculation. It's a general result based on Hilbert, checked by Hilbert series calculation, I think.
Huh. So somehow maybe you want to say that there's some conditions under which you get a fundamental group from these n framings that you can get rid of by making a non-simply laced edge or something. Okay.
So Paul was asking about the case of inverse to 4.
Mm-hmm.
You could compute the Hasse diagram as simple expression. Right, so the first case would be grade 2.
So this quadruple bond is
So that's just the nilpotent cone with the 4 arrows.
okay.
But now you're gonna change it to a quadruple bond to get the covering. That's what you're saying.
So that the quadruple bond is like a twisted FNA 2.
Yes.
So
So the slice, the corresponding slice will be A2, which is what you expect, what you told us.
Yeah, so I guess this seems to match what you told us about the Hasse diagram for.
So the next, so you do subtraction to
So Chunhao will do the subtraction.
1 to 2 with
So in other words, this is supposed to give another realization of all of these
now
y
it's the
events.
remaining part of the A4 what's the
Right.
A3. Does Paul see this?
Does that match what you have?
yeah, I mean what's below this, the bottom 3 nodes, that should be just the closure of the sub-subregular orbit in SL4. So yeah, there's an A1 and then an A3. Yeah, that is what that says. Yeah.
And I think if this is true, this can be generalized to any if-n Grassmannian slices, right?
Mm-hmm.
Yes.
Hmm.
How did you do the subtraction here?
So we subtract this to get this.
Mm-hmm.
Right.
This node is for rebalancing.
Uh-huh. And
So the
then
top diagram, what would be these two steps? What would be the first step? To go to the subregular.
Sorry.
so you subtracted this, you see.
Subtract this and
Yeah, I
you
understand that.
no.
But without the arrow, just a straight quadruple bond, which you've got in the diagram for the nilpotent kind of SL4. There's also a quiver subtraction for that, right? Which will take you to the subregular orbit and then to the sub-subregular.
Yeah. You mean the subtraction for this?
Yeah.
Yeah.
So you have A minus 1. And
I can't quite see. Yeah, okay, but what is the quiver? Yeah. So that's fine.
Here it's
two and one.
Okay.
Good.
One here and two there.
or can make it into a
Right.
Then you subtract one more. Okay, yeah, fine.
Here is the same as here.
Mhm.
And
So it this fits all of what you said, what you told us.
I see. So and so are you saying that somehow this thing you're subtracting here is supposed to correspond to the Y4?
right.
Yeah, in general, if you have 2, 1 with the name, that's the Y.
2, 1 with an N is the YN, you say. Oh, there's another realization of the YN. Which was not mentioned in the talk, I guess.
Yeah.
That's in Julius' paper.
Ah,
Yeah, and then of course they have these two, or the J33 and J32, which is where you've got 3 nodes, and they expect these to produce isolated singularities.
Right.
And so, I mean, there's a general principle that if you have, say, a minimal nilpotent orbit closure with an action of a dihedral group, then you can take a slice inside the minimal orbit, and this is just going to look like a vector space over that dihedral group. So the question is, what does your Q factorial terminalization look like? Well, it can only be isolated if it's dihedral 6 or dihedral 8. That's just follows from these Y of n. If n is greater than or equal to 5, then this doesn't have a resolution. So anyway, so then J33 and J32 are examples where if you look at the strata, you've got some quotient singularity or something which in codimension 4 looks like a quotient by a dihedral group, which is either dihedral 6 or dihedral 4, which is just a Klein 4 group. So you can kind of resolve those things, and the only, or you hope that the only singular points left is the 0, and I think that's what they expect. So
What are J33 and J32?
yeah, these are 6-dimensional singularities that, in fact, you have a whole family J, I, but it's only, I think J2 is something like an A3 singularity or something. And you can also get a G2 singularity, but the J33 and J32 are probably isolated.
Right.
And they get the Hilbert series, and who knows?
Ah. This is supposed to be related to this Y event. I think this is generalizing.
I mean, one thing that struck me just on the way to work this morning was you could play this game. So dihedral group is GNN2. Well, you know, in the classification of complex reflection groups.
Right.
So you could have GNN3, for example.
Yeah.
And this argument that I gave before says the Q factorial terminalization can only have an isolated singularity if n is less than or equal to 3. So you're somewhat restricted, but I mean, that's like, that might, so I'm interested in the kind of classification and or what singularities you can obtain. And so that's one way you might be able to find new isolated singularities.
I mean, the Q factorial terminalizations for the 4-dimensional things will always have isolated singularities. I'm confused. What do you mean?
But this is dimension either 4. Yeah.
Ah.
So in general, if you're dimension 6, then
you won't have isolated
it
singularities.
won't be isolated. Yeah.
For the Q factorial terminalizations, they will not have isolated.
Exactly. Yeah.
So they'll have these 4-dimensional singularities, and what will they be like these Y of n's, or what will the 4-dimensional singularities you get then?
That's then you're down to something like the classification.
So I mean, presumably we can try to understand some picture for what the 4-dimensional Q factorial terminal singularities we get are.
Yeah, I think that's the next key step. Whoever's going to do it, I think Gwyn had some ideas for tackling this classification problem, but at the moment I'm kind of interested in just trying to find new examples.
Okay. And what was the relationship between doing this quiver subtraction for the nilpotent cone and for the cover then? So you're saying that when we do this folding, then now this subtracting this 2, 1 has the same effect as subtracting both of these two?
All right.
Is that going to work for general n then? I guess.
Yeah.
So that would be a good indication that this is supposed to be correct.
It's another consistency check.
Yes, because yn is the cover of that part, right?
So you either subtract the 1, 1 here, and then you get this and then you get the n minus 2 here. And then you're gonna always subtract. And then you're always gonna subtract.
Have n minus 2 and family 1. Next one.
Right. And then you want to
Which
subtract.
is the equivalent for the subvalue now.
Mm-hmm.
And the next subtraction would be the line CN.
Right. With the next subtraction, and that's going to be the same as just subtracting a 2, 1 on the non-simple base one.
Yeah.
I see. Okay, so it's a good consistency check as well. Did you want to? You had a different. We probably have to go though. Did you have you had another question for Paul though, right? That said yesterday. Should we?
The one which I just asked about the E7.
Oh, okay, all right.
So in general, so I guess Paul does not encounter A3 in that. What can you say about AN?
What can I say about?
Just ask Chungtao.
So is there any result about minimal AN quotient Z2? And where the global symmetry is changed into SO type.
Is there any result about it?
Quotient with
C2, which turns the A-type symmetry into SO. So it alternates.
Sorry, what was the last thing?
So it changes the AN symmetry to SO.
Yeah.
That's one.
Or SO n plus 1.
So
Taking the minimal. What's the fixed locus for this Z2?
So I can tell you that it embeds into, I mean, any one of these involutions, you got SLN is equal to SON plus a space that I'll call sigma, right? And so if you look at the S2 action, it's +1 -1. And this means that SLN over S2 embeds into SON cross S2 of this space. And so the same thing is true of AN -1 over S2. It fits in there. And the degrees 2 and 4. So yeah, so you can say what some of the first, well, the Hilbert series is going to be 1 plus half n -1 c squared plus, and then I'm not sure, something in degree 4. Is that the sort of thing you would want to know?
Yeah.
Yeah.
Mm-hmm.
Okay, I can think about this because there's a condition, if you look at the S2 action, it's +1 -1 over S2. And this means that SLN over S2 embeds into SON cross S2 of this space. And so the same thing is true of AN -1 over S2. yeah, I'm not sure whether it's just the sum. I'm not sure what. I'd have to think about what the degree 4 terms might be.
What do you mean by this S squared sigma n?
Symmetric square. Just the vector space. So you take the symmetric square. I mean,
What is sigma n?
it's so if SON is the anti-symmetric matrices, sigma n is the symmetric one.
And now when you
It's
modify sigma 2, then you're going to embed into something larger. Now you're going to embed into the symmetric square. Then.
Yeah, so for the A2 over S2, this is explicit SL3 is equal to SO3 plus. Now this is isomorphic to SL2. So what is the complement? What is S4V?
I see.
So it means A2 of S2 embeds into SL2 plus S2 of S4V, which turns out to be a bit messy, but sorry, I keep hearing my voice, it's a bit disconcerting.
So basically, you're writing out the generators for this similarity, and then at some point you're going to have the relations, and you're going to be able to get a Hilbert series. Is this the idea here?
Yeah, although you want to identify something, then for this case, for example, it's just an orbit closure, but
Right, and they just the agents just.
Which orbit?
Oh, right.
It's an orbit closure. Which one is it?
yeah, SL2, but then you need the scaling action as well. So in one of my recent papers where we show the isomorphism with the slicing type E7, it just comes down to you have the right vectors on each component. You just need one representative of that open orbit and you're done. So, and I think you could do this in general, but that doesn't give you the Hilbert series. So for the Hilbert series, I'd have to think more carefully.
But it's not just an orbit closure, I guess, when we take this quotient, it's something complicated. Could be.
I mean, you can show an isomorphism of varieties if you know they're both orbit closures of the same thing.
Can you complete the minimal two in the presentation?
I have a meeting in 7 minutes. So
Okay. All right.
Thank you very much.
Thank you very much.
Thank you very
Let's
much.
all thank Paul then.
It's great.
Thank you.
thanks. Bye.
If you have any thoughts for our seminar for the autumn, let us know. Okay, Paul. Any ideas?
Yeah.
Thank you.
Okay. Thanks. Bye.
Is he coming to Boston?